well-rounded presentation on the subject of the history of FischerTropsch. It's exciting for me, after doing work in this area for some 25 years, to see now FischerTropsch and GTL being commercialized all over the world. And it just seems like, hey, maybe some of that research paid off after all. Well, I'm going to focus today on the history of cobalt catalyst design, and I appreciate Mark's presentation, his thorough coverage of the iron. The heart of any catalytic process is the catalyst, and I'm going to review with you the history of cobalt catalyst design, because that catalyst design then plays a very important role in the design of the overall process. And when we talk about the history of cobalt catalyst design, it spans about 90 years, and I've divided that timeline into 5 historical periods. Period 1, the discovery. Period 2, commercial development. First period from 1913 to 1928. The second one from 1928 to roughly 1949. And then we have the Iron Age, Sasol, and the retreat from cobalt from 50 to 75. And then the rediscovery of cobalt in the 1970s and 80s. And then finally GTL and the return to cobalt starting about 1985 to the present. Well, these periods are somewhat arbitrary. I guess they match somewhat what Tony presented earlier, but there is some overlap. Now, I'd also like to share with you some observations from the early work. We've been doing some translation of some of the early documents, and of course getting on FischerTropsch.com, and I'm going to talk about some of the observations from the early work that I think were ignored or in the meantime have been rediscovered, and we'll talk about some of the important advances and why, possibly why they happened. Now, I mentioned that cobalt FischerTropsch catalysts have been under development for about 90 years, and in that period of time we have seen substantial improvements in the materials and the design of the catalyst. In the early stages, we began with an unsupported cobalt oxide or cobalt oxide on asbestos, and this has now evolved to a very sophisticated and well-designed material containing about 20% cobalt, anywhere from 0.3 to 0.5% precious metals, and a rare earth stabilized support, typically alumina. Now, the catalyst design itself was, of course, in the early periods, pretty much a trial and error process. And now, in the latter stages, or the latter, or more recent history, we find our design evolving now to computer-assisted nanoscale design. Now let's focus on this first period, the period of discovery from 1913 to 1928. In 1913, a patent, a German patent, was awarded to BASF. And in this patent, they report the production of hydrocarbons on a cobalt oxide at 120 atmospheres and 300 to 400 degrees centigrade. Now, there's some controversy as to whether the BASF people actually produced hydrocarbons or discovered FischerTropsch. First of all, and going back to the original patent and helping in the translation of that, I find that there is really no definitive evidence in the patent that hydrocarbons were produced, nor do they mention the amounts or the kinds of hydrocarbons that were produced. And the conditions themselves of 120 atmospheres and 300 to 400 degrees centigrade are adequately severe to cause maybe production of hydrocarbons on the reactor surfaces. Now, in the years subsequent to this patent, we know that Hans Tropsch and Franz Fischer investigated the production of hydrocarbons on cobalt and other catalysts. And in 1925 to 26, they announced the production of paraffins in measurable amounts at 1 atmosphere and 220 to 250 degrees centigrade on unsupported cobalt, copper, and cobalt catalysts. Now, these are definitely conditions under which we could say catalysis is taking place, and there were measurable quantities, quantitatively reported in their 1926 patent. Now, I'd like to share with you some of Pickler's perspectives from his 1952 review regarding this first period. First of all, he tells us that the successful development of liquid fuels from syngas at the Kaiser Wilhelm Institute was a result of cooperation among many scientists, but Fischer was the, quote, spiritual center of the work. And in that first publication of Fischer and Tropsch in the spring of 1926, this generated a great deal of interest among catalyst researchers. In fact, there was quite a bit of surprise that there could still be so much to learn about a simple molecule such as carbon monoxide when obviously much more complex hydrocarbons have been discovered. Pictures here of Professor Franz Fischer and Dr. Hans Tropsch. Their publication in 1926. Go ahead. And in this 1926 publication, we find a number of, well, according to Pickler, a great many facts that will prove to be important in the later development of catalysts for FischerTropsch. First, that the iron, cobalt, and nickel are the most effective catalysts in hydrocarbon synthesis. Cobalt, most active for production of hydrocarbons, nickel for methane. That carriers such as zinc oxide and chromium improve CO conversion and prevent the sintering of the metals. Addition of small amounts of alkali were observed to favor selectivity to liquid hydrocarbons. Copper improved production of iron, and syngas needs to be free of sulfur. Now, in their 1928 paper, Fischer and Tropsch provide additional insights. Potassium carbonate is the best promoter for iron, best level around 0.5 to 1%. But that alkali poisons cobalt catalysts, that the most effective catalysts are prepared by thermal decomposition of nitrates on porous carriers. Hey, this is a statement I've seen in a lot of recent patents. Conversion of carbon monoxide and iron favors formation of CO2 and on cobalt water. So it appears that Fischer and Tropsch knew an awful lot about this process. They worked very hard. Now we come to period 2, the commercial development from about 1928 to 1949. And here we see the development of the cobalt thoria support on Kieselguhr catalyst. and the medium pressure synthesis. And continuing now with Pickler's perspectives, Fischer and Koch from 1928 to 1934 developed precipitated cobalt thoria kieselguhr, which became then the standard catalyst for the next 40 years. Was used in commercial plants during World War II to produce gasoline and diesel for the German war effort. Fischer and Koch found an optimum temperature for reduction of the catalyst of about 365 degrees centigrade. 5 to 20 hours reduction produced most active catalyst. Thoria increased average molecular weight of the hydrocarbon product, and optimum temperature for reaction was about 190 degrees. Now, in 1935, Fischer reported selectivity data for cobalt and found that the reaction products are mainly straight chain alkanes with a cetene number of 105, and at that point indicated this was an ideal fuel for diesel engines. Fischer and Pickler in 35 to 36 found the optimum operating pressure for cobalt catalysts, their cobalt catalyst, to be 5 to 20 atmospheres. Now, under these conditions, the catalyst was more stable than at 1 atmosphere, and the selectivity for saturated liquid hydrocarbons was higher, and this defined then a route to paraffins and diesel oil. We see here now the productivity of the cobalt thoria kieselguhr catalyst in grams per cubic meter, plotted as a function of atmosphere, and we see a breakdown of the different product cuts. Gas decreases as a function of increasing pressure, as does gasoline, whereas diesel goes to a maximum at around 8 atmospheres, and then paraffins up around 15 atmospheres. You can see that there's a large productivity here of the paraffins under those high pressure conditions. And here we see the product distribution breakdown at 1 atmosphere and 7 atmospheres. It's amazing to me that these people were able to get such good product distribution data, considering the techniques, the analytical techniques they had at that time. Now we have capillary columns and all kinds of wonderful tools, which they didn't have. But looking at these data, they are very consistent with what we observe in modern times with our more sophisticated techniques. Now, what you see here is you go from 1 atmosphere to 7 atmospheres. The light products, the fraction decreases, gasoline decreases, and of course you get more diesel fuel and waxes. Now, following World War II, there was a technical oil mission that a group of scientists that were sent by the Allied forces to Germany, where they interviewed some of the German scientists, including those at the Kaiser Wilhelm Institute. And in a 1945 report by Dr. Vladimir Hensel of the Combined Intelligence Objective Subcommittee, he reports that the best cobalt catalyst is still the cobalt thoria on kieselguhr, that its optimum reduction temperature and time of 365 degrees centigrade and 4.5 hours, that the reduction is carried out at a gas flow rate as high as possible to keep water vapor above the catalyst to a minimum. Now, that's an important point that we'll come back to later. Now we come to period 3. After the war, there was concern about oil reserves running out worldwide, and there was considerable development based on the German work in the United States and and elsewhere in South Africa. And in fact, just at the point when some of this work had resulted in construction of a plant, for example, in Brownsville, Texas, then we have the discovery of new oil resources in the Middle East, and because of the abundance of low-cost petroleum, this leads to the shutdown in R&D in the U.S. and elsewhere, except in South Africa. And there we have Sasol producing fuels and chemicals using the coal-based FTS on iron catalyst, which Mark Dry is so expertly reviewed. Maybe this looks familiar, Mark, but that's the Sasol complex. I believe that's Sasol 2 and 3.
Yep.
Yeah. Go ahead. Yeah. Now we come to the part of history where I was involved. In 1972, I finished my PhD at Stanford, and in 73, I joined the faculty at BYU. And it was in 1973 that we had the Arab embargo, a wake-up call to the world that maybe we need to have a synthetic petroleum industry. And so there was a reaction in US and Europe, and we see two kinds of important activities. The first of these is a lot of scientific work that was done in rediscovery of iron and cobalt catalysts for FischerTropsch. But now we have some additional value added in the form of measurement of specific activities for CO hydrogenation. And at the same time, we begin to see the development of high activity, high metal surface area cobalt alumina catalysts promoted with precious metals and basic oxides. Now let me share some of the highlights of this period with you. In 1973, actually it was 75 when the paper came out, Van Nuys reports turnover frequency data for CO hydrogenation on various group 8 metals, including cobalt. And during the period from 1975 to 1989, many of us enjoyed substantial support from the Department of Energy, universities and companies for synfuels research. It was the heyday of synfuels research. And FT research was intense at oil companies, including Gulf, Exxon, Mobil, and Shell. And FTS was also a hot topic at catalysis and syngas conversion meetings, including that wonderful syngas conversion conference that we held every year in Kingston, Ontario. And that's where I met Mark Dry and a lot of the other experts in the area of FischerTropsch. All of this intensive research led to the elucidation and support promoter dispersion and surface structure effects at places like Gulf, Exxon, BYU, and many other laboratories, using a lot of sophisticated methods and tools, or at least more sophisticated than had been used before. And we see the development of activity structure relationships and design concepts for FT. And in the next slide, what we see is some of the design concepts that were pioneered by David Trim and Jim Richardson. This is a triangular concept for catalyst design that was published, pioneered by Richardson. What you see here is that catalyst design is an optimized combination of interdependent mechanical, chemical, physical, and catalytic properties. And there are always trade-offs. For example, there are trade-offs for porosity. Increased porosity decreases strength but increases activity, for example. And so all of these properties need to be optimized. Now let me share with you some specific results that were obtained at some of the laboratories that focused heavily on cobalt. Gulf Research in the early 80s, Kobolinsky, Kibbe, and Pennell. Pennell was my first PhD student. And when he got to Gulf, he hit the ground running. And that group was very productive. They focused on the preparation of high surface area, high activity cobalt alumina catalysts. They initiated work on ruthenium as a promoter and the use of basic oxides. As you read their patents, you find that they had a pretty good fundamental understanding of several design principles, which they describe very well in their patents. This includes high purity, high acidity, low acidity, high surface area supports, which prevent or minimize the formation of methane, but maximize the formation of an activity of your catalyst. Low heating ramp during reduction, the use of basic oxides to lower support acidity, correlation of high activity with high hydrogen uptake, and optimal reduction temperature around 350. Now that sounds familiar. In our laboratory at BYU, I had a number of students work with me on many different aspects of cobalt catalysis over a period of about 15 years, starting in about 1976 or so. And we developed methods for measuring cobalt dispersion, hydrogen chemisorption to measure active site density, and a oxygen titration to measure the extent of reduction. I think these have become standard techniques now for catalyst characterization of cobalt catalysts. My students and I were able to get a better fundamental understanding of metal support effects, dispersion, and surface structure, and the role of support surface chemistry, and more recently, the problems associated with hydrothermal breakdown of the support. This shows turnover frequency data or activities based on sites, site density for 1, 3, 10, and 15% cobalt on alumina catalysts. And these specific activity data were obtained around 225 degrees centigrade. What you see is a very large increase over 3 orders of magnitude in specific activity, and for the 15% with increased loading, and what you see is the 15%, you have a very high activity. Now, in a study by Johnson et al., and this was a collaboration with Wayne Goodman, and then at Sandia National Labs, we looked at the effects of dispersion and surface structure on the specific activity. And what you see here is the turnover frequency plotted as a function of dispersion over the complete range of dispersion. And this included cobalt catalysts prepared from decomposition of carbonyls with the support dehydroxylated at the temperature in degrees K shown there. And over a range of metal loadings, and we have polycrystalline cobalt that I worked with when I went down to Sandia to work with Wayne Goodman, and cobalt tungsten single crystals that one of my student Byron Johnson worked with Wayne Goodman. And what you see here are 2 important trends. For catalysts of higher loading, well-reduced catalysts that have an extended reduction of greater than 60%, the specific activity is independent of dispersion from essentially 0 to 100%. On the other hand, for poorly reduced catalysts, less than about 50% reduction, and low metal loading, we see that the activity decreases with increasing dispersion. And we were able to show this is due to a support effect. It's not a structure sensitivity. Now, in this work by Johnson and coworkers, We followed up on some of Rule's observations that activity appeared to correlate with extent of reduction. And indeed what we found is that specific activity reaches a limiting value as you increase percent reduction from about 40 up to 90%. Now, these are more recent data in our, from our laboratory where this is George Huber et al. And what we're comparing here are the temperature programmed reduction spectra for a platinum promoted cobalt on silicate catalyst and compared with the unpromoted catalyst, the blue there for the unpromoted, the red for the promoted. And what you see is a significant shift in the peaks for reduction to lower temperatures with the addition of the platinum promoter. Now, you can't talk about this this period of development without talking about the important developments at Exxon, which included a lot of basic work by Iglesia, Fiato, Solid, Reyes, more than about a dozen papers and 20 plus patents. I'm not talking about all the Exxon patents, but the ones that focus on catalyst design and involve a fundamental understanding of things like activity, correlation of activity with cobalt dispersion for suite of catalysts, effects of noble metal or precious metal promotion in enhancing reduction of cobalt and minimizing carbon deposits, the effects of support and precious metal promoters on in situ reducibility, and the development of quantitative models describing the effects of reaction, reabsorption of olefins, pore diffusional transport, particle size, and impregnation depth on selectivity. Here are some of their activity data. These are actually mass-based rate activities as a function of cobalt dispersion for a suite of catalysts prepared on different supports, albeit at relatively high loadings. And so the support effects are minimized, and what you see is a very good correlation of activity with hydrogen uptake. Now that's important because that means you can use hydrogen uptake as an indicator of activity. In Iglesias' 1997 review, he talks about the work of Iglesia and Reyes in developing a model showing the effects of dispersion, metal loading, and other catalyst physical properties on the selectivity of cobalt. Now, if you start at low metal loadings and relatively high dispersion, the C5 plus selectivity is found to increase with decreasing dispersion and increasing metal loading. Now that's due to the elimination of metal support interactions. But at high metal loadings, greater than 10%, and low dispersion, less than about 0.05%, C5 plus selectivity increases with increasing dispersion and or increasing metal loading, and this is due to an increasing extent of olefin reabsorption. And in fact, these workers developed a structural parameter chi, which reflects the extent of olefin reabsorption that can be used to correlate C5 plus selectivity with catalyst structure. Now, chi, as you see, is a function of the radius of the catalyst pellet or thickness of the catalyst layer, the void fraction, the density. It's directly proportional to the density of cobalt sites per unit area, and inversely proportional to the pore radius. Now, what this means then is that chi, and hence olefin reabsorption, and C5 plus selectivity increase with increasing cobalt site density, either due to increasing the cobalt metal loading or the dispersion. And at the same time, the probability of chain termination of methane decreases, because what happens is that you're more likely to get olefin reabsorption And this actually inhibits then the termination to methane. And what we're going to see in the next figure is that indeed we see an increase in C5+ selectivity with increasing value of chi through a maximum, and there's a magical value here of about 200 times 10 to the 16 reciprocal meters. And then it decreases, and the reason it decreases is then you get into diffusion-limited arrival of CO at the sites, and the result is now the rate starts to go down. And similarly, you go through a minimum in methane production. And so what this does is it provides a basis then for adjusting the structure of the catalyst to get the maximum amount of C5+ selectivity, minimum methane selectivity. Now here's some data from Iglesia and co-workers in 1993 showing that just 0.15% of ruthenium added to the catalyst significantly shifts then the reduction of the catalyst to lower temperatures. Well, now we come to period 5. This is GTL and the return to cobalt, starting in about 1985. Now what we see is that in the 80s and 90s there were a large number of patents claiming active, selective, stable cobalt FD catalysts, catalysts based on new compositions, precious metal, and rare earth promoters, and stabilized supports by Shell, Exxon, and Sasol. Some of the precious metal promoters include palladium, platinum, rhenium, and ruthenium. The rare earth promoters include oxides of zirconia, lanthanum, gadolinium, and titanium. And you have silica stabilized with zirconia, titanium with silica, and what you see is that there are ways then to hydrothermally stabilize the support. At the same period, we see third generation cobalt catalyst being used in a commercial Shell middle distillate plant in Bintulu, Malaysia, and in an Exxon demo plant down in Baton Rouge. Conoco develops a new catalyst with a team of about 80 scientists and engineers after testing about 500 candidates. And so these are examples of tremendous development that have taken place. We have some more scientific studies. Goodwin et al. Studies zirconia, lanthanum, and ruthenium. Some 20+ studies in a dozen different labs on the effects of preparation and pretreatment on the activity, selectivity, and extent of reduction of cobalt silica catalysts. How am I doing on time? Okay, well, I'll hurry along. Well, as a result of all of these activities, we now have a basis for a rational design of cobalt FT catalyst. And I kind of summarized all that information in this busy slide here. It's something maybe you can look at later on the internet, but let me just point out a couple of these factors. Here are the desired catalytic functions, like high activity. These are the proven catalyst component or structural features, such as high cobalt surface area, high extent of reduction of the metal, high cobalt site density, moderate dispersion, and optimum value of chi. And here are the critical aspects of preparation and pretreatment and design. And they include, for example, a high surface area support, low temperature drying, slow reduction, high space velocity, high metal loading, addition of the precious metals, and optimum particle size and catalyst distribution. Well, I won't go further, please. But all of this then leads us to a state-of-the-art cobalt FD catalyst, which I propose involves about 15 to 25% cobalt and 0.1 to 0.5% of precious metals, 1 to 3% rare earth oxide, and extended reduction above 80%, a dispersion around 8 to 10%, and a stabilized alumina, silica, or titanium, preferably the alumina, with a BET surface area of 150 to 250 square meters per gram, and a productivity of 1 to 2 gram of hydrocarbons per gram catalyst hour, and a methane selectivity of around 5 mol%. Now that's what you'd like to have. And in a very interesting study by Okatsi et al., they actually prepared different catalysts based on the various patents, and then compared their properties, BET area, hydrogen uptake and dispersion, and their productivities. And what you see is that the catalysts with high BET areas, high chemosorption uptake, and relatively high dispersions around 9 to 10%, the productivities are indeed in the range that you would like for a commercial catalyst. Whereas if you don't have those properties, you get much lower productivities. Now, there are some things that we learned from history. One of them is that nothing is new under the sun. That is, that history repeats itself. And as we go back and look at the early literature, what we find is rediscovery of some aspects of science and technology that it occurs in 30 to 40-year cycles, but it's always better the second time around because we have better tools. That we can learn something of worth from the old literature if we read it, and that too many don't make the effort and reinvent the wheel, and that FischerTropsch synthesis falls in and out of fashion about every 10 to 15 years. So it was popular in 1985 and then fell out of favor. Hey, just wait, it will become fashionable again. Now, some other things that we picked up on in our literature work, some aspects of technology practiced by the Germans and Americans in the 40s and 50s have been now, in the last 25 years, repatented. The cyclic prices of oil and gas, as well as new discoveries, constantly threaten the development of FischerTropsch synthesis and GTL, but the hardy, tenacious, hardworking, and patient will probably survive and do fine. And by the way, in the ultimate paper that you'll get to see, we've listed examples of some of these earlier developments, like rare earth halide promoters and the use of thoria and optimum reduction temperatures, etc. Well, just a word about the future. In the future, I predict that we will see more sophisticated preparations, colloidal methods, leading to more uniformly dispersed active selective catalysts. The role of precious metal promotion needs to be understood, and this understanding could lead to more efficient use of precious metals. The development of a microkinetics modeling accompanied with theoretical calculations could be used to better understand the effects of promoters and how to add them to the catalyst. So there's still a lot of work to be done on the design. By the way, these techniques have been used in the recent development at Halder-Topsoe of a steam reforming catalyst. An example of a new colloidal preparation is the work of Sun et al. Reported in Science, where they reported a new synthesis of iron platinum nanoclusters on silica having finely controlled diameters, plus or minus 5%, in the range of 3 to 10 nanometers, and we see some of those on the next slide. Here are the 6 nanometer clusters. You can see that they're uniformly sized and distributed. These are 4 nanometer clusters from their HRTEM. Now, in summary, I'd like to say that each of several important advances in FT catalyst design was accomplished by a group of scientists or engineers, but it would not have happened without the leadership and inspiration or genius of one or two key members of the group. A number of important observations relevant to catalyst design emerged from the study of early literature, including preparation, pretreatment, active components. A number of these observations were rediscovered and repackaged in the last 25 years. 3 generations of cobalt catalysts have been developed in the last 90 years, and a 4th may emerge in the next decade. Now, these are some of the important advances in cobalt catalyst design. I don't have time to talk about those, but what I do want to do is acknowledge, first of all, Steve Levinus for his encouragement and willing assistance, and Centrola for financial support of our translation review project, and the students Nick Cieslak, Cody Nelson, and Tom Valdez, 3 really sharp undergraduates who are working with me on this project. Thanks very much.
Thank you, Calvin, for giving this excellent overview of what happened with cobalt catalysts over the last, well, 80 years.
Yeah.
Quick questions before we move over to Ben? This one?
Yes, I have a question, might be not related directly to this, but I heard a statement last year that cobalt catalyst is regularly used for synthesis gas derived from natural gas. Why ion catalyst from natural gas?
Yes.
An ion catalyst is used for synthesis gas derived from cobalt. Is it true?
Yes, that is true, that the cobalt catalyst is more ideal for the syngas that is produced from natural gas, which has a 2-to-1 ratio. And that's because cobalt favors the production of water instead of CO2, whereas iron produces its own hydrogen through the water-gas shift reaction because it's active for the water-gas shift, and produces mainly CO2. And so you can operate with a lower hydrogen to CO ratio in the case of iron, and it is better suited for the low hydrogen to CO ratio from coal synthesis gas.
Thank you. I'm just wondering why Sasol is focusing on ion catalyst, not cobalt catalyst, while the syngas they have is from natural gas.
Well, I think I know the answer, but I'll let Mark field that one.
So you have a question?
Yeah.
Why Sasol is focusing on ion catalyst, not cobalt catalyst, while the syngas you have is from natural gas, not from coal?
Well, the way they produce the synthetic gas, it is a 2-to-1 ratio anyway, so there's no problem with the ratio.
So it can be used for anything.
And I think from discussions with the people at Sasol, in the past they've used iron, now they will be using cobalt in some of their new plants.
Yeah, I mean, the original reactors were all designed for iron. You couldn't put cobalt in and they'd blow up too much heat.
Thank you.
Thank you very much, Calvin. Now that we're all balanced again, we know now about the iron side, the iron aspects of Fischer-Tropsch catalysis and the cobalt side. You need the tools to actually convert the feed gases in reactors with this catalyst that just have been discussed. And to